Here is another module to discuss. It is all about waves. Welcome to Engineering Physics. A wave is some sort of a disturbance which travels and transports energy from one point to the other without transporting matter. Let's take a boat for example. The waves will only make the boat move up and down and provide energy, but they do not move it to their direction. There are two general classifications of waves. Mechanical waves are those which require a medium such as water or air to propagate. The other classification is electromagnetic waves, which can propagate even in a vacuum. Examples of electromagnetic waves are light waves, microwave, infrared waves, X-rays, ultraviolet rays, and radio waves. Moving further, mechanical waves can be further categorized based on the movement of particles in the medium and energy transfer. Let's look into the first category. We call waves moving perpendicular to the direction of the wave propagation as transverse waves. An example of this is sound. Longitudinal waves, on the other hand, let the particles move to the direction parallel to the wave propagation, just like water waves. We are going to discuss more about these waves in the next slides. Based on energy transfer, standing waves are those which do not transfer energy and momentum, and in contrast, progressive waves are those which do. A spring motion is an example of longitudinal waves. Note that the particles move parallel to the propagation of the waves. The fundamental parts of longitudinal waves are the amplitude, which is taken as the farthest distance between a particle to the equilibrium. Compression is the part where particles are held close together, and rarefaction or expansion is the area where the particles are somehow farther each other. The wavelength of longitudinal waves are measured between two successive compression areas. Transverse waves have their particles moving perpendicular to the propagation of waves. In the image, particles bounce up and down while the waves move horizontally. Let's check the parts of the transverse waves. Crests are the highest points the waves were able to attain, and trough would be the lowest points. There are also nodes, which are particles or points which do not move away from the equilibrium, and antinodes are those which get farthest from the equilibrium. Amplitude is still measured from the equilibrium to the farthest distance taken by the particles, or simply it is the distance between the equilibrium to the antinode. This time, wavelength is measured as the distance between two crests or troughs, or even at any point as long as one wave has occurred. Frequency for waves will still be the number of waves in a certain period of time, and it is still the reciprocal of period. Speed of wave propagation is taken as the frequency multiplied by wavelength, which is denoted by lambda. There are different modes of vibrations according to materials involved and ways of having such objects in the system. Let's start off with the string, which is held at both ends. In such case that the string is restricted in both its ends, like a guitar string, the two ends will be certainly having nodes. So let's say that we have a string tied at both ends, whereby the distance between these ends is length L. And then we pluck it to give us an antinode. The first instance is what we call fundamental or first harmonic. Note that the whole length of the string will give us half of the wavelength, so we can say that lambda is twice the length. Frequency as velocity all over lambda will then be v all over 2L. The second harmonic frequency show a complete wavelength for the whole length L, so the frequency will be v all over L. The third harmonic will be creating three sets of antinodes where L will be taken as 1.5 lambda, or we can say lambda is 2L all over 3, and the frequency is given as 3v all over 2L. From the derivation, you might have already noted that each harmonic is an added half of wavelength, so we can figure out an expression for the succession of frequencies as number of waves multiplied by the fundamental frequency, or n times quantity of v all over 2L. The string velocity is also computed as the root of t all over mu, where t is the tension of the string and mu is linear density, which is further computed as density multiplied by cross-sectional area of the string. Density of the string can be taken as its mass all over its volume or its specific gravity by water's density. So plugging in this formula for velocity will give us a modified formula of frequency as n all over 2L times the root of t all over mu. Let's check this basic example. Transverse waves travel with a speed of 22 meters per second in a string under tension of 5 newtons. What tension is required for a wave speed of 30 meters per second in the same string? The first setup has 22 meters per second for a string tension of 5 newtons. By using the formula for velocity, which is root of t all over mu, again, t is tension on the string and mu is taken as linear density. Then, 22 meters per second is equal to root of 5 newtons all over mu, where mu will be taken as 5 newtons all over 22 meters per second squared, which would turn out as 0.01033. Knowing the linear density of the string, we can then solve for the tension required to shake it with 30 meters per second. So with the same formula, root of t all over mu, we can place the given to make it 30 meters per second is equal to root of t all over 0.01033, and tension is solved as 9.297 newtons. Another scenario to check for mode of vibration would be a rod which is clamped at one end. In this system, the clamp end is going to yield a node and the free end can give an antinode. And making the same analysis, we can say that the wavelength will require 4 lengths, so the formula becomes NV all over 4L in Hertz instead of 2L like we had earlier. For a rod system, velocity will be taken as the root of y all over rho, or that is a root of Young's modulus with respect to the density of the rod. The rod can also be fixed at its midpoint, and by making it vibrate, both ends will be antinodes as they are both free and open for waves. From the image, we can conclude that the case will be like the strings, where lambda is taken as twice the rod's length and its frequency is still equal to n times fundamental frequency, or that would be n times v all over 2L. Another system to consider is through an air column. Let's start with an open pipe where both ends are open. So as shown in the image, both ends will be antinodes, which would have similar analysis with the string once more. So L is half of lambda, and frequency is taken as n times fundamental frequency, or that would be n times v all over 2L. This time, velocity is taken as the velocity of air, which is given with the formula 332 plus 0.6 times temperature. The other deviation of the air column is having one end closed. So just the same as the closed end will yield a node, and the open end will be an antinode. Shown are the fundamental, second harmonic, and third harmonic. This is similar to the rod clamped at one end, so we would need to have 4 of the length to make one wavelength. The second harmonic will show that to keep the conditions of nodes and antinodes, L will become 3 of lambda all over 4. And the third harmonic requires L to be 5 of lambda all over 4. So in the formula, N will be taken as 1, 3, 5, 7, 9, and so on. For velocity, it would still be computed the same as 332 plus 0.6 of temperature. Check out Module 9, Fluids at Rest.